When working with vectors, you need a way to describe its characteristics, whether that be by length, angle, projections, distance. All of these need some sort of tool to be able to actually measure against. And that's exactly what a coordinate system is. By the book, it says that a coordinate system is a way to describe a vector accurately. And in this course, we're going to cover 3 different coordinate systems that are in 3 dimensions. But just realize that there are multiple other systems which exist for different applications. Mainly in this course, like I said, we're going to be focusing on 3-dimensional coordinate systems, but the relationships within these systems and how they function are based off of very basic 2-dimensional concepts. So to start, we're going to look at a coordinate system which hopefully you are very familiar with, the rectangular coordinate system. So one of the key factors in almost any coordinate system is this idea of orthogonality. Now, in math, you could think of orthogonal as a fancy word for perpendicular. It's not exactly, because orthogonal isn't just used with geometric terms like lines and planes. It's also used with functions as well. But in a 2-dimensional rectangular system, we have 2 special lines that we use which are orthogonal to each other, and we use them as the core reference to any point within the given space. We know these lines as the x-axis and the y-axis, but what these lines really are is a collection of every point which forms a line where within that space where x is equal to 0, which is our y-axis, and where y is equal to 0, our x-axis. And what's interesting is that within these coordinate systems, it can be said that any point can be represented by the intersection of 2 orthogonal lines. And since we know that x and y are orthogonal, we can set these x and y values and we get lines which intersect at a given point. For example, we have a point at the location 2, 3, and by looking at the graph you can see that it is at the intersection of x equals 2 and y is equal to 3. This 2 and 3 we call coordinates, and it corresponds to the location of that point. And just a little thought experiment before we move on, using this ideology of intersecting lines at right angles, will this same idea and visualization work with polar coordinates? So think about it with 2-dimensional polar. You have a radius and an angle. At what point is there 2 lines that intersect orthogonally? You have a curve and a line. So I just want you to think about that before we move on later in the chapter to other coordinate systems that are based off of polar. So when we extend to 3-dimensional systems, such as the rectangular system going into 3 dimensions, we can still use this process of orthogonal things that intersect and generate a system which we can reference. With 3 dimensions, however, if we hold one of the values constant, so like x equals 0, y equals 0, or z is equal to 0, instead of getting a line, we get a plane. So in 3-dimensional rectangular systems, it's comprised of 3 intersecting planes, which can be seen on the right. And the question always comes to be, and will always be a source of students losing points, is labeling these axes correctly. So one of the most useful tools you have in front of you is your right hand. So if you were to hold it out in the way that the picture below shows, with your index finger pointing out in front of you, your middle finger kind of going parallel to you, and your thumb going up, you can see that if you put X on your index finger and Y on your middle finger, that wherever your thumb is pointing is going to be the Z direction. And this can be seen in this graph, and if you wanted to try this out, it's a little hard to bend your wrist this way, but if you put your index finger on the X-axis, your middle finger on the Y-axis, and your thumb along the Z, it fits that right-hand rule. In a rectangular system in 3 dimensions, we're still given in the same X, Y, Z fashion, but just remember that it's the intersection of 3 planes. So, for example, point P is actually the intersection of 3 planes, X equals 1, Y equals 2, and Z equals 3. What happens when we start representing these points as intersections of planes and lines is we get an interesting phenomenon we can exploit to make a differential element. Think about it like this. You're bored on your computer and you're on your desktop, and you're idly trying to pass time, and you're clicking on your desktop and dragging so it makes a box, and you're dragging in all different directions. This actually is a good example of what a differential element is all about. You have a point which you're starting at, which we're going to call P, and you're dragging the cursor to a destination point, which we're going to call P prime in this case. And if you look at what happens, it actually makes a square in 2 dimensions. It actually makes an area. And the sides of this area can be determined if you know the initial point and the final point. And you can also figure out the length between the 2 points using all that information. But let's extend this out into 3 dimensions. Now imagine that you're using Microsoft's HoloLens, which works with augmented reality, and you can control elements on the screen by basically pinching in the air and dragging in free space. So there's an X, Y, and Z component to your movement. So let's say that the initial point that you're starting at is represented as P, and it's given the coordinates X, Y, Z, just some arbitrary numbers, and that your location, your destination, is P prime, which is X plus dx, Y plus dy, and Z plus dz. And the reason that this is called a differential element and dx, dy, dz are differentials is because those values are extremely small. And if you remember back to Calculus 1, when you're learning about integrals and doing Riemann sums, you're shrinking the area infinitesimally small. If we look at the 6 planes which actually comprise P and P prime, so there's 3 for P and 3 for P prime, instead of getting a square, we get a volume. And this volume is, for rectangular, known as a rectangular parallelepiped. And from geometry and trigonometry, which you're going to have to dig out of the recesses of your mind, maybe to figure out these problems, you can see that it has these different properties. For example, the volume, given as dV, differential volume is equal to the differential x, differential y, differential z, multiplied together. The surface areas of each respective surface is just the product of the 2 lines that comprise its surface. So for example, this top is just dx and dy multiplied together. Now in the back here, let me see if I can get my mouse back. In the back here, there is our point P, which was our initial point. There's a line that goes from P to P prime, and we can find the length of this utilizing Pythagorean's theorem a couple ways, and you end up with the square root of dx squared plus dy squared plus dz squared. That's one good exercise you could do at the end of this video, is actually figure out where that equation came from and derive it for yourself. And actually deriving all of these for yourself would be a good practice in getting you back in the mindset of trigonometry and geometry.